Okay, in our next video, we've got another essential skills video, and we're going to look at evaluating experimental data. So we're looking at concepts around random and systematic error, precision, accuracy, scatter, and some of the issues caused. Parallax is one example of those. Some of those things that can affect our experimental data, and how we'll go about evaluating the quality of our experimental data from an experiment. So when we assess a evaluation in a practical investigation, I reckon there's four main things that we are looking for. We're looking for a description of the sources of uncertainty or error. I like the word uncertainty because error, I have a few problems with that word, but error is widely used and it's not completely wrong either. So the words uncertainty and error can sort of be used interchangeably. So we're looking at sources of uncertainty. We're looking at evidence of uncertainty in your results. We're looking for you to make an assessment of your data and the quality of your data. And we're also looking for you to identify improvements that could improve, if you like, the quality of your data or the quality of your results. I think, and I'll talk about this probably more in the next slide, this isn't necessarily the way you need to structure your evaluation. I think there's several valid ways you can structure evaluation, and depending on the experiment, depending on your results, and depending on individuals, different ways of structuring an evaluation will suit some people better than others. I think I'm keen to sort of get away with everyone basically using the same evaluation in basically every prac, whether it's physics or chemistry or biology, and they all do sort of start to sound the same, and I think sometimes we miss some of the subtlety of each experiment and showing some of that higher order evaluation skills when we start writing those generic ones. So I'll talk a little bit more about how we structure these, but I think in terms of what needs to be in them, this is a good starting point for that summary. And we'll now go and really dig down into each of these things and what are we looking for in your evaluation to cover each of these four categories. Okay, so we need to start off by looking at our sources of uncertainty or error. We need to classify them into two types, random and systematic. So our random errors tend to be our measurement errors or our judgment errors. So things like the parallax error, if your eye isn't exactly level with the scale that you're reading on, or judging a reaction time, or judging a colour change, or that's probably more in a chemistry experiment. But all of those things that involve us judging and measuring, sometimes we might be too high, too low, too fast, too slow, so they can go either way, hence the word random errors. We also need to classify, the other type of error is our systematic error, and these tend to be due to problems with the calibration of the equipment and or maybe faulty design in our experiment. So if we have if we had a balance, and when we put 50 grams on there, it said 48 grams, it wouldn't matter how many times we did the experiment. If that equipment wasn't calibrated properly, we're not going to get the correct result. And, faulty design, I know we've just been doing the circular motion prac. So if we had a situation where we had a lot of friction in our system, that's going to, in a sense, provide extra force that's going to affect our results every single time, hence systematic. So faulty design, things that are problems with our design can be also sources of systematic error, as well as things that are not correctly calibrated. So how do we look for evidence in our results of experimental uncertainty or error? And once again, the way we look for random and systematic error is different. Random error is generally associated with scatter in our results. So, for example, if we had 3 measurements here, let's just say they were time, it doesn't really matter. We can see we've got a scatter here from 19.07 to 19.87. So we've got a scatter of about 0.8 seconds. Whereas at the bottom, we only go from 19.38 to 19.44, so 6/100ths of a second. So there's less variation across these, less scatter, so these results might, all the other things being equal, being regarded as having more scatter, therefore, less scatter. These ones have more scatter, therefore more random error. Particularly in physics, where we're often looking for directly proportional relationships, we can also look for scatter around our line of best fit. So the line here in green, all the points lie nicely on our line of best fit. We'd probably say there's low scatter there. Here, we've got a lot of scatter around our line of best fit. So we'd have a greater amount of scatter, more random error. Systematic error, we can do a couple of things. We can compare to a true value. So if we know what the true value, so what the value should be in the experiment, we can compare that with the value that we obtain to make an assessment about whether there is likely to be systematic errors. When we're looking at directly proportional relationships, we can also look at the y-intercept, because that's often evidence of there being some form of systematic error in your experiment. And the reasons for what will cause that y-intercept to not equal 0 will be different in various experiments, but it's also a good key that maybe you have some systematic error. The assessment of the data. Really what we're mainly looking here is making a decision about the precision of your data and the accuracy of your data, and basically looking at those two things in combination to make, is it a valid result? Could you make a valid conclusion based on that data, on the basically precision and accuracy of that data? So just a quick reminder, those who've had me in stage 1 will probably remember shooting Nerf guns and talking about precision and accuracy. So this idea of precision being that your result is very repeatable, we just talked about that. So low amount of scatter is equal to a high precision. However, in this case, close to the true value, if we were shooting a gun, we should be hitting the target in the middle. So you can see here, this would be like a calibration error with the sight, so we would have low accuracy. Here we'd have low precision, they're all over the place, so we weren't a very good shot probably. But if you averaged them all out, it would be in the middle. So we could see by averaging there, we would have actually got a reasonably accurate result. Low precision and low accuracy, basically we're scattered all over the place, and when we average those all out, we're not near the centre of the target either. So that would be indicating both random and systematic errors with our experiment. So we would have both a low accuracy and a low precision. What we would really like to be in an ideal world, and we can't always get there, is have high precision and high accuracy. So we're on the true value and we're spot on. All our trials are very close to each other. So next, I won't say finally, because you don't always have to have improvements last. In general, the improvements are going to be quite specific to each experiment, but doing more trials and averaging will reduce the effect of random errors. Also, often improving our measuring techniques or equipment. So, making sure our eyes are level, using some sort of video rather than just relying on reaction time for the start of an experiment, using equipment that has a greater precision. So if we were trying to measure something that happens in sort of tenths and hundredths of seconds with a clock on the wall that's really only going to have a resolution of about 1 second, we're not going to be able to get a very precise result. We're going to have more random errors because we're having to make more judgments. So there's more opportunity for judgment and measurement type error. In terms of our systematic error, we generally need to be able to repeat the experiment with independent equipment, or ideally even use a completely different technique. And probably a little bit more than that, we need to actually compare that. So in a sense, if we use two different techniques or two different sets of equipment and get the same value, we can have more confidence in our accuracy that we're near a true value. But if we use two different techniques and we get two different values, then we probably need to go to a third technique or use a third set of equipment and see if that starts to favour one result more than other. So over time we can build up a better picture of what would be a more accurate result. This is often harder to achieve in terms of a practice that we'd do in the lab. I guess the other thing which I didn't mention here, which I should mention and I will add straight away, is the other thing that we can do to improve our and prove our experiment and minimise the effect of systematic error is to calibrate our equipment. Now, hopefully we did that if we could have easily calibrated it during, the first part of the pracs, but that can't always happen. The other final thing I'd really like to mention here is we really need to focus on significant sources of error or uncertainty. There's a lot of potential errors with any experiment. We could come up with a really, really long list of uncertainties for any experiment, but it's really important that we focus on the ones that are most significant, are most likely to affect our results. So, for example, talking about the calibration of a stopwatch, I've never come across a stopwatch that's so poorly calibrated that it's maybe likely to affect a set of results. So that's probably an example of a systematic error that, you might want to mention, but I wouldn't be spending a lot of time evaluating. You need to focus on the ones that are most significant. So please remember that. So finally, a few ways about how we might structure an evaluation. So we might do it by source. So we might talk about one source of error, classify it as random or systematic, talk about the evidence from our results that shows that type of error, make an assessment about whether it's affecting our precision and or accuracy, and talk about how we might improve it and minimise the effect of that error or eliminate that error or improve our experiment. And then we might move on to source 2 of error and go through a similar process. So we go through and evaluate by source. Obviously, we'd probably want to have a balance of random and systematic errors if we do it that way. We might do it by type. So we might talk about random sources of error and the evidence, or we might talk about our results and the evidence in them of an error, and then talk about what those random sources are. So we could interchange both those first two categories, and then we might make some assessment of our data and suggest some improvements related to, for example, random sources if we did that first. And then we could use a similar process and talk about the systematic errors. So we look at the two different types of errors separately. Or we could do more along the lines of, this is sort of probably what I did in the last slide, talk about our sources of error and the evidence for those in our data. And once again, we could reverse those two. Then we might talk about assessing our data and some improvements we could make. Or we might even talk about the improvements to our data and then talk about, relate that to assessing our precision and accuracy and potentially how that would improve. So I think there's just 3 to start with. I think there's probably some other logical structures that you can use. That's what I meant by the bit in green, or any other logical structure. And I just want to finish. I should have probably wrote this on the last slide, but I ran out of space. It's really important that you remember to focus on the most likely and most significant sources of error or uncertainty in your experiment. So, I don't really want to see a list of 25 possible sources of error, of which 24 are not likely to have any meaningful effect on your precision or accuracy, and therefore the validity of your results. So yeah, that's it for evaluating experimental data.